In this video, we see how the electron configurations of elements are responsible for the periodic or repeating trends in chemical and physical properties that can be found in the periodic table. The term used to describe these trends in the periodic table is periodicity. You may recall earlier we were introduced to the periodic law. When elements are arranged in order of increasing atomic number, elements with similar chemical and physical properties occur at regular or periodic intervals. And by now we should also be familiar with the periodic table, and a description of it could be something like this: an arrangement of elements in order of increasing atomic number in which elements of similar chemical and physical properties are placed in vertical columns, known as groups. And we now know that the reason for these similar physical and chemical properties is due to similar valence shell electron configurations within each of these groups. Here we now introduce the idea of periodicity, which can be described as the variation in physical and chemical properties of elements based on their position in the periodic table. And again, we now know the position of an element in the periodic table is due to its outer shell or valence shell electron configuration. And so therefore the position of an element in the periodic table can be used to predict physical and chemical properties and predict many useful trends in the periodic table, including atomic size, ionisation energy, electron affinity, the formation and stability of ions, and therefore the chemical formulas of ionic compounds, as well as the size of ions. We'll start by looking at the trends associated with the physical property of atomic size. Roughly speaking, the size of an atom is determined by the size of the electron cloud and therefore by the size of the outermost occupied orbitals. The quantum mechanical description of atoms suggests that their shape is roughly spherical, the result of the combination of overlapping orbitals in three-dimensional space. For example, a 1s orbital overlaps with a 2s orbital, which overlaps with the three 2p orbitals, to produce a roughly spherical shape. We can therefore quantify atomic size in terms of the radius of a sphere. This figure shows a plot of atomic radii measured in picometers versus atomic number for elements in the first 6 periods, up to element radon, which is number 86 on the periodic table. Dashed lines show that, in general, the size of atoms increases as we go down a group of the periodic table. For example, we can see the group 1 alkali metals or the group 18 noble gases both increase in size as we go from period 1 to period 2 to period 3, period 4, etc. The solid lines with dots show that, in general, the size of atoms decreases across a horizontal period of the periodic table from left to right. For example, as we go from lithium to neon from left to right across period 2, we see that atomic radii decrease. And the same can be seen for period 3, going from sodium through to argon, with the same general trend being observed across all the other periods. The other way of saying this is that atomic sizes increase from right to left across a period. There are a few anomalies to these general trends, but by and large they hold true for most elements. These trends in atomic radii can be explained on the basis of the number of protons in the nucleus, the number of electrons in the electron cloud, and how these electrons are distributed through shells, subshells, and orbitals. For example, as we traverse across the second period of the periodic table from lithium to neon, we note that the number of protons in the nucleus, the atomic number, increases and that the electrons are added into the same n equals 2 shell. The increased positive nuclear charge draws negatively charged electrons within the same n equals 2 shell closer to the nucleus, resulting in decreased atomic radii from left to right across the period. By the time we reach neon, its 10 electrons have completely filled the second shell. When we go to the next element in period 3, that is sodium, we note that the 11th electron needs to be placed in the n equals 3 shell, and specifically the 3s subshell, which is higher in energy and larger than any of the n equals 2 subshells. Therefore, as we go down a group in the periodic table, atomic radii tend to increase because electrons are added to shells and subshells with a higher n value and therefore larger sizes. And so we can start looking at an overall representation of the periodic table and start to superimpose some general trends on this diagram, where we see that atomic radius increases as we go down a group and increases as we go from right to left across a period. The next property we will consider is a chemical property called the ionisation energy. Ionisation energy refers to the energy required for the formation of cations, positively charged ions, from neutral atoms by the removal of electrons. We know that electrons within orbitals can be promoted to higher energy levels by absorbing energy. For example, electrons can be promoted from lower energy levels to higher energy levels if there are unoccupied orbitals available. However, if the energy absorbed is high enough, past the n equals infinity level, the electron can be ejected from the atom to form a positively charged cation. The ease with which electrons can be removed from atoms has a significant effect on chemical behavior. We can represent this ionization process with a chemical equation showing that, for example, a sodium atom can absorb energy equivalent to or greater than 495 kilojoules per mole, and the uppermost 3s electron will be ejected from the atom to form the Na plus ion plus a free electron. This graph shows how the ionization energy varies with atomic number, and we can see that the general trend is that ionization energy decreases down a group, as we can see here with the group 18 noble gases, and increases across a period, as we can see here for the period 2 elements going left to right from lithium through to neon. The trends for ionization energy are the reverse of the trends for atomic size, and in an inverse way, both are related. The smaller the atom, the tighter the electrons are held to the nucleus and the harder it is to remove them. Hence, ionization energy increases as atomic radii decrease. Electron affinity is the next property of atoms we will look at. In some ways, it can be considered the opposite of ionization energy, as it refers to the energy released when a neutral atom in a gaseous state gains electrons to form an anion, a negatively charged ion. When a chlorine atom, for example, picks up an electron to form the chloride ion, energy is released. This energy change, minus 349 kilojoules per mole for chlorine, is called the electron affinity. The minus sign indicates that energy is released in this process and that a chloride ion is more stable and has lower energy than a chlorine atom plus a free electron. A chlorine atom can therefore be said to have an affinity for electrons. Large electron affinity values, that is, large releases of energy, indicate that a stable anion will be formed. Small negative electron affinity values, or small releases of energy, indicate that the anion will be less stable. And so this table shows the electron affinities for the main group elements. Broadly speaking, the general trend is towards more negative electron affinity values from left to right across a period and up a group. But there are many exceptions to this general trend. Something worth noting is that the nonmetals of group 16 and 17, groups 6A and 7A, have the highest negative values for electron affinity, which explains why they tend to form more stable anions than metallic elements on the other side of the periodic table. Elements in group 2 and group 18, or 2A and 8A, do not form stable anions at all, as placing additional electrons into their electron clouds requires these electrons to go into higher energy orbitals, thus absorbing energy rather than releasing it. We're able to superimpose another set of trend arrows on our periodic table, indicating that in general, electron affinity increases across a period from left to right and increases as we traverse up a group. To complete the picture of general trends in the periodic table, we are going to add two more properties to this diagram. The first refers to metallic and non-metallic character of elements, and we can see that, in general, elements in the upper right of the periodic table have more non-metallic character, while elements at the bottom left have more metallic character. And the last property to superimpose on this diagram is the property of electronegativity. Now, electronegativity is actually a bonding concept, and we will deal with it in much greater detail in later videos in this series. It is actually a measure of an atom's ability to draw valence electrons to itself within a chemical bond, and as we can see, electronegativity increases from left to right across a period and increases as we go up a group. So, this completed diagram here is a useful guide to being able to predict properties of elements based on these general trends and based on their position in the periodic table.